slide. Now let me hit these couple of announcements. You've heard them all before, so I probably could have done them before I got launched. But there we go. Math team meeting, as far as I know, today at 3. Birmingham West Campus, room C100. That's in the Science Building. And Mr. Rossi is the coach for that. And they're having a great time and learning a lot of math, so that's good. They also meet Fridays at noon. Tutoring, again, I emphasize, I don't think either of you will need it, but if you do, it's there. What's even more so is it's there for you to tutor, because I think y'all would be great tutors. And the other announcement, this really isn't much of an announcement, but it seems forever since I was on the Birmingham campus on a Friday when I'm supposed to have office hours there. This Friday, knock on wood, I should be there. Okay. No more doctor's appointment, no more infusions, no more meetings. Hopefully I'll be there Friday from 7:45 to 11:45. Now, watch no one else be there because it's the weekend before spring break, but I don't know. We've had a dean that likes to call a meeting on the Friday before spring break late in the afternoon. It's a lot of fun. Okay, I may not be there if that's the case, but we'll see. All right, last time we got up to the mean value theorem. I may turn on the projector. Watch this stuff. So let's pick up where that is. This is a mean value theorem, okay. All right, Rolle's theorem that we did last time can be used to prove another theorem, and this is the mean value theorem. And it's taking the projector a long time to warm up. It must be scared of the weather too. Here it comes, I think. And it says no signal. You know, these things drive me nuts. You would think that projector could figure out where the computer is without having to be hooked up to it. But, you know, it's just so picky. They require you to be connected. And there it is. I was up here and had plenty of time to do all this, but I don't know why I forgot to do it. I think I got distracted somehow. All right, Rolle's theorem can be used to prove another theorem, the mean value theorem. What the mean value theorem states is that if f is a continuous function on some closed interval, a to b, differentiable on the upper interval, a to b, okay, then there has to exist a number c in a to b such that f prime of c, the derivative of f at that number c, is exactly the same as the slope of the secant line between a and b, okay? A and b are the endpoints. So if f of a is here and f of b is here, and that's the secant line between them. That means somewhere in between a and b, you have a point c whose tangent line is exactly parallel to that secant line, okay? And let's see how much they go into it. If not, I will. Oh, they don't go into it at all, okay? There is a proof in the book with a nice figure. And I don't know why in the previous books I've used from this guy, this publisher, and everything, they put the figures in here. And this book has left them out. But if both of you have your books, that figure 312 illustrates this. There's f of a, f of b, a f of a b f of b, and there's a secant line in between. The curve goes between. It has to be smooth and continuous, okay? Continuous, they told you, smooth means differentiable. In between those 2 points, there's going to be at least one place where the tangent line is parallel to that secant line. What's that?
Y over x minus y over x.
Yeah, it's kind of like that. Basically, got a smooth continuous function here. Anywhere find, and it's not necessarily the average. If you do this slope here, you may have to be way over this way, or this slope you may be way up down there. But someplace in there, there's got to be. And basically, Rolle's theorem said if those two endpoints are the same, then the slope has to be 0, which is parallel to that. This says if the two endpoints are not the same, the slope is still parallel to that. Excuse me. Because, if you think about it, the slope at this point is something. So the figure in the book was very positive. Okay, very positive here. Then it went up, decreased, and then became very negative and got there. So anywhere you're going to be in here, it's kind of like that slope. Not quite an average, but that I see where you're sort of getting that concept from. To be something that's in between there. And basically, let's see if the way they do it here. I've seen it proved this way. Do you another function? Well, I won't go into it in a second. You can read through that. Now, let me remind you, both of you are pre-engineering, not math, or? Huh?
Computer science.
Oh, you're computer science, okay. And are you?
Yes, we're pre-engineer.
Pre-engineer. So you probably aren't as interested in the proofs as a math major would be, maybe. But the proof is there, and you can read through that and see. I think it's fairly straightforward. It looks possibly a little more complicated than some of the proofs I've seen, but I don't think it's too bad. There is a little blurb. I was trying to see now why he's on here. Oh, first person to prove it was a famous mathematician, I think French. No, born in Italy. But held this position in the court of Frederick the Great in Berlin, so in Germany. Back then, I think it was considered the Holy Roman Empire. I can remember my 12th grade English teacher said, and it wasn't holy, it wasn't Roman, and it wasn't even an empire. I don't know why they call it that. So anyway, so he was a court mathematician. Actually, to me, he looks fairly Italian in that shot, and very famous mathematician, probably the best of his time. And so if you're interested in pursuing him or how he came up with the mean value theorem, a potential paper topic. Hint, hint. Okay. All right, let's move on to example 3, which we do have in the slide set. And this also, as you'll note right under example 3, it says see larsoncalculus.com for an interactive version of that type of example. Oh, man, my sleeves loosen stuff up, I'm afraid. So this may be helpful in, it won't prove the theorem, but maybe help you see it a little bit better. Here's your function, f of x equal 5 minus 4 over x, okay? And it says find all the values of c in the open interval from 1 to 4 such that f prime of c is the same as the slope of the tangent line, f of 4 minus f of 1 from the endpoints over 4 minus 1. Okay. So there's the problem. Now, before we get started, here's the open interval 1 to 4. Could that have been 0 to 4? Or is there anything special about 1 to 4?
I don't know, because that would have changed your whole average, wouldn't it?
Yeah, I mean, it would be a different average, but could you have posed the problem?
Oh, because it would have had a 0.
Absolutely. It's not defined at x equals 0, and it needs to be continuous in the closed interval and differentiable in the open interval. That would have been differentiable in the open interval, but not defined at the endpoint. So how could you even do a slope between something that's not defined yet? So that's one reason they chose 1 to 4 here. Negative 1 to 1 would not have worked, because then you would have had a discontinuity in it. I mean, yeah, so you have to be careful, and this does fit the bill. It is continuous and differentiable anywhere between 1 and 4. Okay? It says find all values of C in the open interval blah such that F prime of C is equal to that. So there's a few things we've got to do. You tell me which one you want to do first.
We could plug in the endpoints.
Okay, we've got to figure out what alpha 4 is, for instance, so let's do that. Let me get my pen activated. Okay, so F of 4 is equal to 5 minus
4 over 4.
Yes, which is?
1.
Okay, 5 minus 1, which is 4. Okay, we got that one. And the other? Alpha of 1 is equal to what? 5 minus 4 over 1, which would be 4, and that's equal to 1. So you would almost think this was the identity function, wouldn't you? Just choosing those two values, but of course it's not the identity function. That secant line is the identity function, though, between those 2 points. So now we've got those. What else do we need to do before we can really plug and chug too much? That's a good question, or good answer to any question in this course. Oh, take a derivative. So let's do F prime of X first, and then we'll plug in C for that. And what will that give us? Frankly, I would rewrite F of X first. That'll be 5 minus
4x to the negative 1.
Perfect. Okay. Now take the derivative of that.
That would be negative 4x to the negative 2.
Okay. Here you have a coefficient of negative 1 and an exponent of negative 1. Multiply those two together and you get positive, okay? 4x to the minus 2, which we'll go back and write in without negative exponents as 4 over x squared. And then F prime of C is equal to 4 over no, C. Just plug in C. Yes, in Spanish, right? C. Right, okay. C squared, right? Okay, now, so let's see what we've got here, folks. We've got F prime of C, which is 4 over C squared, equal to, what was your alpha 4? 4 minus alpha of 1. 1 over 4 minus 1. Any guess what that's going to turn out to be? Second? 3 over 3, and what that's going to be? 1. So here we have our equation. 4 over C squared is equal to 1. Now we need to find all the values of C on that interval, which makes that equation true. So how could we solve that? Plug in what? 2? Is that what you said? Yeah, just looking at it, that would give it to you. To be a little more analytical about it, let's multiply both sides of the equation by c squared, right? Okay, and these, the c squareds go out. Now, the only time that's not fair to do is if c is equal to 0, because you don't want to multiply both sides of the equation by 0. You lose all meaning of your equation. But c can't be 0, can it? Because, you can't divide by 0 anyway. So this gives you 4 is equal to c squared. And then what would you do? Sure enough, 2 is a solution, but what's another one? What's that? Okay, it's the only one that works. But say again? Yeah, take the square root of both sides. I'm going to reverse the sides. That makes c is equal to, what's that? Okay, but anytime you take square root of both sides of the equation, you have to do a plus or minus 2, because both of those will work, right? But, as you said, 2 is, positive 2 is the only answer. Why is it minus 2? C must be in that interval. So 2 is the only one. But that's why I went through that to let you see. There could be, because they said, find all the values. Well, minus c would be a value, except it's not on the open interval. So yes, we do forget about the minus sign, because that would be outside the domain, and positive 2 is your one and only solution. Okay? And there you see, Justin's here. All right. We just are finishing example 3 on page 177 and 3.2. 3.2 is Rolle's theorem and mean value theorem. Last week we did Rolle's theorem. This week we're doing mean value theorem. Okay? Now, I wish, well, let's see. Maybe they will have this one. So, all right for me to erase this? Okay? Then let's see if they show the figure on this. Hopefully they will. Slope of the secant line through 1 alpha of 1 and 4 alpha 4 is 1. Just like you determined, okay? Note that the function satisfies the condition of the mean value theorem, that it's a continuous function on the closed interval, a differentiable function on the open interval, so everything works there. You didn't include 0 in your domain, so you're okay. That is, alpha is continuous on the closed interval, differentiable on the open interval. So there exists at least one number c, according to the mean value theorem, and c 1 to 4, such that alpha prime of c has equal 1. So alpha prime of c is 4 over x squared. That's equal to 1. And then that implies x equal plus or minus 2. Plus 2 is on that interval. Minus 2 isn't. Throw out the minus 2. And here's the figure, finally. Okay? Here's your secant line between 1, 1 and 4, 4. And like I said, that is the identity function, because it goes right through the origin and right through all those points where x and y are the same. However, that's the only 2 places it crosses this function, so it has really nothing more to do. It's just the luck of the draw of what points you picked it. Usually it's your endpoints. But since this is a smooth continuous function here, obviously here the derivative is greater than 1, but up here it's less than 1, and since it's a smooth continuous function, it has to be equal to 1 somewhere in between, greater than and less than. Gotta be. Okay? Because it's a smooth continuous function, the derivative is itself a function and a continuous one. So it has to have that value in between there. Okay? Does that make sense? So I kind of get what you're saying with average, but it's not really average of anything. It's not the average between 1 and 4. You know, that would be 2.5. You know, so that's why I was cringing a little at the word average. But I see what you're saying. The slope kind of averages out, kind of, you know, a little bit. All right. And Nicoma, but you had me with the hair. Okay. It looks nice.
This may be sort of too vague of a question, but like, where is somewhere that you would like use this?
Say if you were doing optimization, say you had a plant in your second.
A rocket or a nuke?
Yeah. Okay. Okay. There's maybe a better one. Okay. You're wanting to. You know this thing is following a parabolic path here, and you want to know when it's going to be at a certain angle, so you can fire the booster and make sure you get out of orbit.
Right.
Yeah. Okay. I was thinking more optimization theory, and sort of industrial engineering type thing. If you're trying to maximize a whole set of variables, you have equipment and personnel and things like this, and how many people it takes to operate it and how much it costs to operate it and stuff, and you're wanting to produce the greatest amount, not the greatest, the optimal amount to get the maximum profit margin, okay? Then, you probably would have all sorts of curves, but, that point, if that point is that point, that value in that, then this could be, that's sort of a stretch, but.
Sort of like your teetering point between profit and.
Yeah. You see, See here, your production is going up quickly, but past this point, it's sort of going down, and therefore you're in the space where you're making maximum rate per amount. Here is less. Your maximum income will still be up here, but your maximum profit is already passed because now it's costing more to make that next increment, though you can make the next increment. Yeah, I made that up. So I hope that's pretty close to true. But all right. So we see who was lying in bed hoping the school was going to be canceled now. No, I'm just kidding. Just kidding. You didn't hear me, did you? Oh, okay, good. All right, we just finished example 3 on page 177 in section 3.2, Rolle's theorem and mean value theorem. This was a example of the mean value theorem. All right. They're skipping example 4, so whoa, goodness gracious. Here we go. Let's us do example 4 here. And this may be an even better example, okay? 2 stationary patrol cars equipped with radar are 5 miles apart on a highway as shown in the figure. Now, do all of you have a book or something you can see the figure? I sure hope I don't have to draw that one for you, okay? As a truck passes the first patrol car, its speed is clocked at 55 miles per hour. 4 minutes later, when the truck passes the second patrol car, its speed is clocked at 50 miles per hour. Prove that the truck must have exceeded the speed limit, that of 55 miles per hour, at some time during those 4 minutes. Wait. Started off at 55, which was at the speed limit, and 4 minutes later was less than that. So you couldn't prove that, could you?
I have a feeling we're going to.
Huh?
So I have a feeling we're going to.
Yes, I think so. And this isn't the one we really were hoping for, that the cops are there using the mean value theorem on you, okay? All right, I doubt it. But anyway, they could be. Okay. Well, let's see what's happening. Okay? What would be your setup then here? Okay? What we know is that and you can pick your time interval to be anything you want to. Okay? So let's say at time t equals 0, he goes past that first patrol car. Okay? And by the way, do these trucks go at smooth and continuous functions? Yeah, they have to. They can't have a discontinuity somewhere. They don't just suddenly go on at 55 miles per hour and then jump to 50. You can't do it. You have to be continuous. You know, the speedometer has every number in between. Okay? And also, they're smooth. They don't have any abrupt angle. They can't be going at one rate and then another rate. So I think we're fairly safely within the confines of this. So, now, here's the deal that sort of sets this apart. When you're thinking of it with your function being the speed, you really don't see how it could be any different. But the function here is really the distance, okay? And the speed is your derivative of that distance, okay? If I can't remember. Yeah, we've done it, haven't we? Yeah, this derivative of distance is velocity or speed, okay? And if not, you'll get it in physics, okay? But what I was saying is we're going to start at t equals 0, and that's when he passes the first patrol car, okay? And his speed is clocked at 55 miles per hour. So let's see, what are they using for speed? They're not. I want to have something. I'm going to use v, even though it's not really velocity, but v of t is equal to 55 miles per hour at t equals 0. Okay? So v of 0, I guess that's probably what I should say. V of 0 is equal to 55 miles per hour. All right, here's Elijah. All right. We were almost every other student. Now finally we got 2 contiguous students. Okay. All right. 4 minutes later, so this will be at t, and by the way, this is 0 minutes. So at t equal 4 minutes, the velocity at time t equal 4 is equal to 50 miles per hour. All right. Now, do you see anything that's a little bit problematic here? Besides the whole problem? No, I'm sorry. Hint, units. What's the issue? Time is given in minutes, but the speed is given in miles per hour. So you either gotta refer to this in minutes or refer to that in miles per minute. Okay? And I don't know which way you would rather go. Do you have a preference? What's that? speed in miles per minute or get the minutes in hours? The minutes into hours. Okay, we can do that. I can do the first one without your help. T is equal to 0 hours. 0 minutes is 0 hours. I feel good about myself, okay? Then V of 0 is equal to 55 miles per hour, okay? But the other one is at T equal, now how do we get 4 minutes into hours? I'm going to do a little conversion here. 4 minutes, we're going to multiply by blank blank, and we're going to get blank hours. We're going from minutes to hours. Now, this is how I do conversions. You don't have to do them this way. To me, this is the most visual and surefire way of doing it, rather than memorizing the formula. Okay, what I want to do first, the first blank here is for numbers. The second blank is for units. And I say, always put the units into place. So you got 2 units here, minutes and hour. One's going to go on top of the line, one's going to go below the line. You tell me which unit goes above and which unit goes below. My minutes and hours. Say again? Say that again. Yes, minutes have to go below the line, and that puts hours above the line. Now you match the numbers with the units. How many hours in a minute or how many minutes in an hour? Second? 60 what? 60 minutes make 1 hour. Now you got it done. So what we do now is divide the denominators, so that would be 4 over 60, which would be 1 over 15 miles per minute. Okay? Well, let's see. Yeah. No. Okay. Oh, yeah, hour. I'm sorry. Okay. Chasten's here. Okay. Well, I'm sorry. It's not miles per hour. It's just hours. Okay. That's how long. I said that wrong. That's how long 4 minutes is 1/15 of an hour. That's all, 1/15 of an hour. So when T is equal to 1 over 15 hours, then your velocity at 1 over 15 is equal to 55 miles per hour. Okay, now we're everything in terms of hours. Okay. Now, how far, this is where what we need to do is get away from speed, velocity, okay? That's not the thing of interest. Really what you need to deal with is the distance. How far, what is your position at these various times, okay? So you let S of T represent the distance in miles traveled by the truck, okay? So S of T is distance traveled in T hours, okay? And by the way, one thing I forgot to say is these two things are 5 miles apart. Now, if I had noticed that, this is real easy to do, okay? If it's 5 miles apart and 4 minutes later, he passed the second place. Guess what, team? Faster than 60 miles an hour, because you can't go 5 miles in 4 minutes, because a mile a minute is 60 miles an hour. So frankly, that's really all you have to do. You don't have to use the mean value theorem, because you look at that and say, ha, he had to be way above 55 miles an hour between those two because he couldn't get from here to there 5 miles in 4 minutes without exceeding the speed limit. No way. Okay. So there's the answer to your question, but they want you to use the mean value theorem, right? It says, prove that the truck must have exceeded, well, I think we just proved it without having to use mean value theorem, but we'll do it. So, S of t represents the distance in mile traveled by the truck, and we know that S of 0 is 0, okay? And we know that S of 1/15 of an hour is equal to 5 miles, okay? Right? Everybody in agreement with that? So there we have a closed interval, right? 0 to 15 is your independent variable, time, and your distance, S, is 5 to 0. So what does that give you? Your average speed, and here we go back to average velocity. So average speed, that's what I'm going to use to represent that, is equal to S of 1/15 of an hour minus S of 0 hours over 1/15 of an hour minus 0 hours, right? And this S up here is 5 miles. Goodness, that's ugly. How did that come out that way? It's sort of like my pen was writing slow. I don't know. 5 miles minus 0 miles over 1/15 of an hour. So that would be 5 times 15 over 1, right? And what's that? Whoa! His average speed was 75 miles per hour, so there's no way he couldn't have been exceeding that in that time. I mean, he had to. In fact, he must have had his CB on, found out there was another cop car out there, so he slowed down real. He wouldn't have done that, would he? No, I must have just made that up. Okay. So therefore, there had to be someplace in between there, and I would even say possibly a couple places where he was going at least 75 miles an hour. But that's all you had to show, was that the average was that, therefore he had to be at least one place in between there he was going 75 miles an hour. That's not even the maximum, that just shows that someplace he was going there. All right. But again, you could just look at it and say, no way he could travel 5 miles in 4 minutes without exceeding 60 miles an hour. This shows he had to been at least 75 miles per hour, at least for one instance there. And I would suggest maybe that wasn't the max. All right, homework exercise. Any questions on 3.2? Homework exercises here, either do 3 or 5 or both. That's up to you. They're both at calcchat.com. Neither are at CalcView. Do either 7 or 9. They're both at CalcChat. 9 is at CalcView. Do any of the odds 11 through 23. They're all at CalcChat, but 13's at CalcView. Then do either 25 or 27 or both. They're at CalcChat, not at CalcView. Do 29, it's at CalcChat, not at CalcView. Then do 31, it's at CalcChat and CalcView. Then do either 33 or 35, they're both at CalcChat, neither are at CalcView. Do 37, It's the only one like that. It's a calc chat. Then do any of the odds 39 to 47. They're all at calc chat. 47 is at calc view. Then do either 49 or 51. They're both at calc chat, not at calc view. And then do 53. It's at calc chat, but not at calc view. There's some exploring the concepts there that you can look into if you'd like, 55 and or 57. Actually, yeah. And then there's also another one, number 59, that you can do. That's more of a applied problem. The others are kind of not quite proofs, but things coming off of the proofs. Then you can do any of the odds 61 through either 61 or 63. They're both a calc chat. By the way, 59 was a calc chat too, none of them are a calc view. And then 65 or 67, they're both a calc chat, not a calc view. And either 69 or 71, they're both a calc chat, not a calc view. 73 and 75 are true false. Be sure you, if you're doing those, understand why they're true or why they're false. That's the main value in them. And then there's some that have proofs 77, 79, 81, 83, and 8. Well, those 77 through 83 are proofs, okay? So do them if you'd like. 85 is then using mean value theorem. That would be probably worth a look anyway. All right, any questions on that? Let's see if I've missed any slides here. All right, I did. I shouldn't have skipped over that, but it's right at the end, after example 4. It says a useful alternative for the mean form of the mean value theorem is this. If f is continuous on some interval a to b, just like it is for mean value theorem, and differentiable on the open interval a to b, then there exists a number c in a to b such that, and basically what they've done here is this. I think it's easier to show you. Mean value theorem said there is a value f prime of c such that that is f of b minus f of a over b minus a, right? So what they did was multiply numerator and denominator by b minus a. So this goes down to b minus a, okay? And that would give us, I'm going to rearrange the order a little bit, f of b minus f of a is equal to f prime. Nope. I thought they were going to write it that way, but they don't. Okay? B minus a times f prime of c, and then add f of a to both sides. And that gives you f of b is equal to f of a plus b minus a times f prime of c. Okay. Which, if you pause to think about it, and this isn't very fair to do because it's not a linear function, but basically that looks like a point slope formula, doesn't it? If you just reverse the order here, f of b minus f of a is equal to f prime times b minus a, which would be m times b minus a. Looks like a point slope formula, okay? Or pretty close to it anyway. That's describing it for the secant line. That is valid for the secant line, but this is saying you can think of it in this term here. And I think I put an extra parentheses in there that I didn't match with a closing parenthesis, so let me take that out. So there's another way you can do it. So it says, when doing the exercises for this section, keep in mind that the polynomial functions, rational functions, and trigonometric functions are differentiable at all points on their domain. So you can use that form if it's helpful. May or may not be. Okay. And then after this, we're through with the section. Any questions on 3.2? I already gave you the homework exercises. So let's discard that. This isn't, oh, okay, good. Wondering what happened to it. Okay, okay. Sorry that I did that. I just wanted to check to see if my last class Thursday, I had to start overloading it because it had bombed out. Okay. Thought I'd already done that. So let's move on to 3.3. And PowerPoint's taking its usual. Whoa! What did I do to lose my video? Maybe when it comes up, it'll come back on, but computer's still hooked up. I didn't unplug it, I promise. Well, that's not working, so let's do this. Goodness, this thing is slow. Ah, there it came back. So, continuing in Chapter 3, Applications of Differentiation. 3.3 is talking about increasing and decreasing functions and the first derivative test. Have I already given you that? No, I'm just kidding. Okay. That's a dumb question. All right. Here are the objectives. We'll determine intervals on which a function is increasing or decreasing. What would give us that? Second? Oh, yeah, sounds like a good answer. Okay. But what about the first derivative will tell you whether it's increasing or decreasing? Second?
First number or the first?
Okay. It's not a hex as opposed to this. What positive? Your answer? First derivative is positive, guess what? Function has to be increasing. First derivative is negative, it has to be decreasing. It tells you, just look at the sign of the first derivative. That will help you know whether it's increasing or decreasing. And then we'll apply the first derivative test to find relative extrema of the function. What were those relative extrema? Maximum and minimum. Very good. Okay. The relative extrema do not count the endpoints. Okay. Those are just the max and mins. So let's first look at increasing and decreasing functions. We will learn how derivatives can be used to classify relative extrema, which is the next part, as either a relative minimum or relative maximum. First, it's important to define the increasing and decreasing functions. So, here's that definition. A function f is increasing on an interval when, for any two numbers, f, x1 and x2 in the interval, as long as x1 is less than x2, that implies that f of x1 is less than f of x2. We did this back in pre-calculus. There's nothing new here. We haven't even mentioned a derivative here. Okay? A function f is decreasing on an interval if for any two numbers, x1 and x2, on that interval, as long as x1 is less than x2, that implies that f of x1 is actually less than, whoa, they said that backwards. That's a greater than, okay? They got your sign wrong, okay? This is the first time I've taught this from this book, and they got it wrong in the book too, didn't they? Wow, this is amazing. And this is the 11th edition. They haven't found that error yet. This is greater than. Yeah. And let me make that correction here too. I'm going to leave it in red. That's greater than f of x2. If it's a decreasing function, when x1's here, x2 there, that means f of x1 has to be greater than f of x2. Otherwise, it would be decreasing. Okay? So that was an error, both in the book and on the slide set. I thought maybe the graphics guy just got it wrong. But no. Okay. A function is increasing when, as x moves to the right, x moving to the right on the horizontal axis, the graph is moving up. It's decreasing when, as x again is moving to the right, the graph is going down. And this function right here is decreasing on the interval, as far as we can see, from negative infinity, as far out here as you want to go on x, and there it's way up here, decreasing until it reaches f at a, x of a, okay, x equal a, f of a, okay, and then it becomes constant from there, and then when it gets to x equal b, f of b is that same value it was at f of a, but then past that, it's going up again, so therefore it's increasing from b to positive infinity, okay? So increasing from negative infinity up to a, decreasing function, constant function between a and b because it's there, and then increasing function, anything greater than b to infinity. Now, I think I didn't have all of you in pre-calculus algebra. I have a few of you, maybe. Yeah, I don't know. I had some. When you're talking about intervals on which things are increasing, decreasing, or constant, when you're talking about the intervals, we usually just leave the parentheses. We don't usually put a bracket here or a bracket there or something like that, or brackets here. We kind of ignore those points in between and just look at the interval itself. Okay? So it's not wrong to include it, but most of the time we just put parentheses there, not square brackets. All right? And here they say it, even though it wasn't mentioned in the definition or anywhere else, the derivative is related to the slope of the function. Because here, the first derivative is negative, here the first derivative is 0, here the first derivative is positive. So that is how we can tell. Whereas before that definition, you had to use that definition only. Now we can just look at the first derivatives and say, we got it from there. We don't need to evaluate all sorts of different function values. Now, as shown in theorem 3.5 below, a positive derivative implies the function is increasing, just like we said. Negative derivative implies the function is decreasing. Zero derivative on an entire interval implies the function is constant on that interval. Notice it's not zero necessarily. It's just constant. Back here in this figure, this is not zero. It doesn't tell you what value it is, but zero would be down here. But its derivative is zero. Okay? The function is not zero. Okay? So here's theorem 3.5. Test for increasing, decreasing functions. Let f be a function that is continuous on the closed interval from a to b and differentiable on the open interval a to b. Okay. This is not what they're intending here, but I'm going to use it. Does this function meet that criteria? Those function here, it is continuous here and defined outside of that. So this is not the best example for that, but I just wanted to point out to you that bigger function there was not differentiable at those points where it changed direction sharply. So, but getting back to what they're getting at. If f is a function continuous on a closed interval, a to b, differentiable on the open interval, a to b, then if f prime of x is greater than 0 for all the x's, not just some of them, all the x's a to b, then f is increasing on the whole interval a to b. If f prime is less than 0 for all the x's on a to b, then it's decreasing on the whole interval a to b. And if f prime is 0 for all the x's in a to b, then it's a constant function on a to b. That's what we saw in that last one. Between that a and b, it was a constant function. The f could not have been outside that a to b. It wouldn't have been the differential. Okay. Now, example 1. This is flip the page. By the way, the theorem 3.5, there is a, what is that code called? I call it a square bar code, but it has a better name.
Quick response code.
Say again?
It's a quick response code.
One more time.
Quick response code.
Quick response code. Okay, QR code is what you told me before. I couldn't remember what it stood for. Okay, you can flash on that and you can get a little bit of interaction there. Okay, and they do have a proof, so that proof probably is there too. And it may be audio visual, so you might be able to hear them talk about it. But on the next page, 182, is example 1. Find the open intervals on which f of x is equal to x cubed minus 3/2 x squared is increasing or decreasing. How are we going to do this? How will we do this? Take a derivative. It sounds like a capital idea. I'm going to get my color back here. Okay. So f prime of x is equal to 3x squared minus 3x. Perfect. Okay. Now, what we're going to be, okay, two things here. This derivative is also a smooth continuous function. Okay? All right? Now that's important because if that was not smooth and it went like this, then, or like this, or anything else, it has an abrupt change there without being a zero derivative in between. But if it's smooth and continuous, then anytime it's going to change direction, it's got to have a first derivative of 0. Very good. Okay. You read my hand. Okay. So that's what we're going to do first. Set that equal to 0 and find out if there are any, and by the way, they said find the open interval on which it's increasing or decreasing. The open intervals on which. But first thing, we're not even interested in that. We want to know where it's changing direction or where that's equal to 0. So how do we determine that? Factor. And what do you factor?
Factor out of 3x.
3x. And what do you have left?
X minus 1.
And that product is equal to 0. Now what two values would make that product equal 0?
0 and
X equals 0 or x equal 1. Okay? Now, if those two places, the first derivative is 0, that means it's not 0 other than that, right? So to the left of 0, it's got to be something. In between 0 and 1, it's got to be something. And to the right of 1, it's got to be something. These two values are the only places it's equal to 0. Okay? So what that means, the function has to be, and this is sort of a new word maybe for you, monotonic, meaning going in one direction only, between before you get to x equals 0, in between 0 and 1, and after 1. Okay? Because if it changed direction anywhere in there, you would have had another derivative equal to 0. We don't. Those are the only two places that derivative is equal to 0. So that means the function is either decreasing before 0 or increasing before 0. One or the other. Because at 0, the first derivative is 0, so it flattens out, and then it's either increasing or decreasing between 0 and 1. It can't be anything other than that. And then between 1 and positive infinity, it's either increasing or decreasing again. It can't be 0 because those are the only two places it's 0. And it can't change direction because that would have to require another. Because it's a smooth continuous function, the first derivative is, it doesn't have any of it. All right, so how in the world are we going to determine? Here are the open intervals, negative infinity, which really isn't a proper thing. You could say negative 453,817 or something like that. Up to 0, you have another interval from 0 to 1, and you have another interval from 1 to infinity, or 7,843,517 and a third, or something like that. Okay? So we know they're either increasing or decreasing there. How are we going to figure out what it's doing there? Because it could be either increasing or decreasing on each one of those. How would we know? Say again? Plug in a value that's something between negative infinity and 0. Let's not use negative 453,815. I don't want to. But what could we plug in? That won't be at that interval. Say again? Negative 1 sounds like a wiener to me. And we're going to plug it into the first derivative function. So f prime of negative 1 would be what? Say again? I hope not, because we found out that only one place is 0. Okay, it's 3 times a negative 1 squared minus 3 times a negative 1, right? What's negative 1 squared? Second? 1. So that'll be 3, and minus 3 times minus 1 is plus 3, and that's equal to 6. So guess what? Yes, positive slope, so therefore increasing or decreasing? Increasing on this one. So here it's increasing. Okay? How about 0 to 1? Okay, we'll plug in a half. Okay? To the first derivative function, f prime of 1/2 is equal to, you could use 0.5 if you prefer, but okay, it doesn't matter. 3 times 1/2 squared minus 3 times 1/2. And what does that give you? Anybody? Help me. I'm stuck here. Hold on. What happens? What's 1/2 squared? 1/4. So that would be 3 times 1/4 minus 3 times 1/2. Okay, what's 3 times 1/4? No. What? Say again? A fourth? 3 times 1/4 would be a fourth. Okay. So you owe me a fourth of $1, and I owe you a fourth of $1, and I'm going to borrow, do it 3 times, and I still owe you a fourth of $1, right?
It's 3/4.
3/4 of it. Yeah, that would be 3/4 minus. Say again? I couldn't hear. Huh?
He said 3/4.
3/4. Okay. Well, 3 times 1/2 is 3/4. Oh, he did the other one. Okay, got it. Okay. Well, what's 3 times 1/2? That would be 3/2. And what's the difference between 3/4 minus 3/2? I'm really not interested in the value. I want the sign. I want a sign. Okay, never mind. It's going to be negative 3/4. You're absolutely right. The deal is it's negative. Okay? Okay? So what does that tell you about between 0 and 1? It's a decreasing function in that interval. Okay? And now we'll choose Clark's choice. What did you want to use before? 2. Okay, let's do f prime of 2. And what is that? 3 times 2 squared minus 3 times 2. What's 2 squared is 4. 3 times 4 is? Say again? 12 minus 6 is 6. So guess what it is from 1 forever? It's positive or increasing function. Okay. First root of it being positive. Okay. Increasing function. Now, we almost could have done that based on what we knew in algebra before. Because in algebra before, we said use the leading terms test. Remember that? The leading term is to a cubic, which means odd power. So yes, it's going like this, or like this. We don't know which. But then we look at the sign of the leading term, and that's positive, so that's going like this. So it has to be increasing from negative infinity to somewhere, and it has to be increasing from somewhere else to positive infinity. So we knew these two had to be both increasing. Okay? What we didn't know for certain is what's happening in here. And frankly, they almost have to be decreasing. It can't be increasing. I guess it could have been this. Increasing to here, then increasing to here, and then increasing to there. But that wouldn't have been a cubic function. That would have been a fifth degree function. So it almost had to be decreasing there. All right. But we didn't quite have enough to know it. Calculus gives us everything we need to know it. All right. Does that make sense? All right, good. Now, I was afraid I was running over. All right. Now, they throw a few more terms in here. All right, let's see what they do. Can I erase this now? Okay. So, note that f is differentiable on the entire real number line, and the derivative of f is that, x cubed. No. Goodness gracious. Derivative is, and then they write the function again. That's not the derivative. They just written it again. Why they would have phrased it like that. Here's what the derivative is. Okay? F prime of x is 3x squared minus 3x. Just what we got. And to determine the critical numbers, I probably should have thrown that term back in because we did it a few sections ago, and that was a long time past. Yes. Those are called the critical numbers. We set f prime of x either what? Where do you find your critical numbers?
Zero or where it's undefined.
Yes, we're at 0 or undefined, so this is a nice, pretty polynomial function that's defined everywhere. So therefore, it's only where it's equal to 0. So we set that equal to 0. And then we found the true, we factored just like we did before. And we found the only two critical numbers were x equal 1 or x equals 0. Is 3 not 1?
I think we'll also say the closing this afternoon.
What time?
Yeah,
At 1?
yeah, closing at 1.
Closing at 1. Okay. That means my last two classes won't be today. So, but I get to go home and let the dog out. Okay. But what you do with this is set each of these equal to 0. Is 3 ever equal to 0? Not in this universe. So no, don't tell me 3 is not. X equals 0, that's 1, and x minus 1 equals 0. Those are our true critical numbers. And we know that those are the only two places is equal to 0, so it has to be increasing or decreasing on either side of those and in between those. Okay, because there are no points for which f prime does not exist, because it's a nice, smooth polynomial function. You can conclude that f at x equals 0, x equals 1 are the only critical numbers. Yeah, we did that. And the table summarizes, don't you love these tables, okay? That first interval from negative infinity to 0, it has to be the same thing everywhere in there. From 0 to 1, it has to be the same thing. And from 1 to infinity, it has to be the same thing. So pick, look at that. They chose a test value of negative 1, 1/2, and 2, exactly what y'all chose. And we found out alpha prime of negative 1, that test value was positive, so it has to be increasing everywhere on that interval. And alpha prime of 1/2, which is what we chose here, was negative 3/4, which is exactly what we found. Negative value, so it has to be decreasing between 0 and 1. And then when you get out there to 2, it's increasing again, so it has to start at your critical value, x equal 1, and increases from there on. And we could have told you that from analyzing the leading term test. At least part of that we did that. Okay. So we've done it. Here is the actual graph of that. It's increasing forever here, from negative infinity all the way to 0. But at 0, it has a first root of 0. And then it's decreasing after that. We knew that because at 1/2, it was a negative value, so it had to be negative everywhere between those two zeros. And then at x equal 1, we knew it had to be a 0 derivative there again. Past there, we found out it was very positive here, so therefore it had to be positive everywhere from 1 to positive infinity. All right, good deal. Now notice what the test didn't tell us. It didn't tell us the values here or here. Where did we? How would we get these values? All it told us was increasing, decreasing, increasing. To get the values, plug the critical numbers back into your function, and when x equals 0, that's 0, that's 0, so it's going to be 0, 0. When x equals 1, that will be 1 minus 3/2, so it will be negative 1/2. Sure enough, there's those two. It's increasing up to there, decreasing down to here, then increasing forever. Okay? So you have to go back to, for graphics, you go back to your function and plug into. All right? Okay. So, example 1 gives you one instance of how to find the intervals on which functions are increasing and decreasing. The guidelines below summarize those steps followed by that example. Okay? As if we needed this, but we'll do it. If f is let f be a continuous function on the open interval a to b. Now before this, we said the closed interval. Doesn't matter, it's continuous. Okay? To find the open intervals on which f is increasing or decreasing, use the following steps. Step 1. locate the critical values of F in between A and B. Okay? Notice we didn't say anything about it being differentiable, F, in that interval, only that it was continuous. So locate the critical numbers of F in A to B. You tell me what they are again?
0 and 1.
No, not in this function. Any old function. What are the critical numbers?
Where it equals 0 or 2.
What's the, yeah.
The derivative.
Right, where the first derivative is either 0 or not defined. Now, if F was continuous and differentiable, then you wouldn't even worry about the not defined. But they did say differentiable, so continuous or not defined on the interval. Those are the critical numbers. Use those to determine your test intervals. Okay? Between A and that first critical number and the first to the next, however many critical values you have there until you get to B. You're not interested in critical values less than A or greater than B, just those in between A and B. Okay? So, at that point, you use those as your test intervals. Okay? Now, determine the sign of F prime at one test value in each of the intervals, just like we did. Okay? Pick a value in between A and that first critical value and plug it in at F prime between the next two critical values, the next two, whatever, until you get the last one to B. Okay? Pick a value in there. Okay? And then you use that theorem to determine whether it's increasing or decreasing. What would determine that? You determine what the value of the F prime here. What does that tell you about whether it's increasing or decreasing? If F prime is positive, increasing, and if it's negative, it's decreasing at those test values. Okay. These guidelines are also valid when the interval is replaced by an interval in the form of minus infinity to B, A to positive infinity, or minus infinity to positive infinity. Works. Whatever those endpoints. Either a negative infinity or positive infinity is not an endpoint. It means it just goes on forever. All right, a function is strictly monotonic. I used that term before. Monotonic meaning on an interval when it is either increasing on the entire interval or decreasing on the entire interval. For example, this function, f of x equal x cubed, is strictly monotonic on the entire real number line because it's increasing everywhere. Now you might say, oh, it's not quite increasing at 0, is it? Because it looks like that's a pretty flat derivative, and it is. First derivative is 0 there. Okay? Take the first derivative, 3x squared, x equals to 0, x equals 0, right? But that's still monotonically increasing because if you go just a little bit this side of 0, it's going to be very, very, very negative. Go a little bit on that side, it's going to be very, very, very positive. Because put a negative number in here, no matter how tiny, 0.0003, or 1 or something like that, and plug that in, it's still going to be negative because it's cubed, and on the other side it's positive, and cube that, it's going to be ever so slightly positive, but still positive. Okay? So it is monotonically increasing. Even though if the first derivative does flatten out at 0, it's never constant. The function is not constant. Awfully close, but never quite. Okay. Strictly monotonic function. Okay? That's what it means. Going in one direction. You know what a monocle is? The planar peanut, where's that monocle? Single lens. Okay? Okay. As opposed to bifocal or something. Okay. The function shown in figure 317, this one here, is not strictly monotonic because there is an interval there. It is constant. It's increasing here, but from 0 to 1, it stays at 0 So that's not increasing here, okay? There it is constant, and then it's increasing there. So that looks a lot like the other one, is not monotonic. This function here is defined this way. Minus x squared from x less than 0 to 0 from x equals 0 to x equal 1, and then x minus 1 squared from anything greater than x is greater than 1. Not monotonic, okay? Never decreasing, but not monotonic, because it is increasing at a part of that.
So
Yeah.
did they just put that together for the example?
Yeah.
Because that's not really a real.
It's a piecewise defined functions, which are real functions. It's kind of construed to do this, but yeah. But I mean, you run into piecewise defined functions fairly frequently. Have you ever gone to mail a package? Okay. That's not continuous like this one, but it's a fixed rate for anything less than an ounce. It's a different rate for anything between 1 and 2 ounces. Different rate because that's a piecewise defined function you use all the time. Some of the old phone plans and things like that were also piecewise defined function. You use a certain rate between 100 and 200 minutes, and then another rate between 200 and 300 minutes. I don't know if any phone plans do that anymore, but they used to. Okay. So yeah, you do run into
That's
things.
called a piecewise defined function.
Piecewise defined function, that's what it means. It's define this thing for this portion of the domain, define this way for that portion of the domain, and define this way for that portion of the domain. And yeah, it was sort of made up here to be continuous, because everything we had required to be continuous. And not only is this one continuous, but the derivatives are continuous. So this is also a smooth function. There's no angles and stuff there. But it's not monotonic. Okay? Even though it's never decreasing, it's not monotonic, because it is constant somewhere there. Sure, that's not going to show up often. I can imagine ever, but maybe somewhere it will. All right. Through with that, let's move on to first derivative test. How are we doing on time? Woo, not long. Okay. After you have determined the intervals on which a function is either increasing or decreasing, it's not difficult to locate the relative extreme of the function, is it? No, because that's what we use to determine those intervals. So it seems like to me we also almost put the cart before the horse here. We found the first derivative where it's equal to 0 first. For example, in that one that we did a while back, the f of x equals x cubed minus 3 halves x squared, from example 1, the function this has a relative maximum at 0, 0. Not an absolute maximum, because everything over here is greater than that. And a relative minimum at 1, negative 1 half. Here, relative, not absolute, because anything over here is going to be less than that. But that's where your relative extrema are, okay? Where your first derivative is either 0 or not defined, okay? Now, why do we know it's a relative extrema? Relative maximum, say. Well, the first derivative was positive on this side of 0, 0, but negative on that side. That had to be a relative maximum. If it's going up and then going down after that, got to be a relative maximum. And here it was decreasing this way. First derivative negative this way, 0 here, and then positive there. Changed its sign, relative minimum, because it was decreasing to that point, increasing after that point, had to be a relative. Okay? So yeah, first derivative. Everything we did before shows us these have to be our extrema. Okay. Similarly, f has a relative minimum. Yeah, I just said that because it's decreasing immediately to the left of x equal 1, increasing immediately to the right of x equal 1. Therefore, so this next theorem makes it more explicit. Do we have time for it? Yeah, I think so. Whew, well, I guess so. First derivative test. Let C be a critical number of the function f that is continuous on an open interval I containing C, sorry. If f is differentiable on that interval, except possibly at C, what does that mean? The first derivative may not exist at C, okay? So therefore, it may not be, it's differentiable everywhere except at C. Then f of C can be classified as follows. If f prime of C changes from negative to positive at C, f has to be a relative minimum. If it changes from negative to positive, it has to be a relative minimum. If f prime changes from positive to negative at C, it has to be a relative maximum. If f prime is positive on both sides of C or negative at both sides of C, then f of C is neither a relative minimum or relative maximum. Okay? And here would be an example. F prime is negative coming down to C, positive at to C, relative minimum. Positive before you get to C, 0 at C, and then going downhill after that, relative maximum. If it's increasing before C and then increasing after C2, it's neither a relative minimum or maximum. Looks like it's going to be a relative maximum here. Looks like it would have been a negative minimum there, so it's a neither. Or it could have been going downhill here, negative on this side of C, but then negative on the other side of C2, neither. Now, later, we're going to call these points, maybe not always, but most of the time, these are going to be called inflection points. We aren't there yet. We're going to get there shortly. This is where you have a first derivative equal to 0, but the signs don't change with the first derivative on either side of that. These are going to be inflection points. Now, they may not be only inflection points, but they will be sometimes called that. All right. Now, there is a proof there. Not very long proof, but there is a proof there. I think we'll start next time with example 2, because I believe we have now officially run out of time. Now let's see if we got far enough along for any homework exercises. I think you can do number 3. It's at calcchat.com. And I'm pretty sure you can do any of the odds 5 through 9. They're all at calcchat.com, but 5 is at calcview. And I'm pretty sure you can do any of the odds 11 through 17. They're all at CalcChat. 13 is at CalcView. And since we haven't done one with applying to the first derivative test, you can stop at 17. We'll pick up the rest of those next time. All right. Any questions? So we'll begin with example 2 next time. Good deal. Okay. Be safe. It actually looks a lot less threatening now than it did earlier, but be safe. There must be a reason they let people go at 1. But yeah, if you're in another class, they'll let you know. Be safe on the road. Get home and stay home. Don't be wandering around if you